introduce today Katharina Jochemko from KTH, and she's going to tell us about the Ehrhart-Theory.
Yeah, thank you very much for the introduction, and yeah, thanks to the organizer for the invitation to speak here. It's a really great opportunity. Yeah, I'm going to speak about Ehrhart-Polynomials of Dilated Polytopes. That's what it said in the program, and then I realized I actually have a bit more time, so I will also tell you a bit about zonotopes. And let me start by introducing our main objects, which are lattice polytopes. So lattice polytopes are the convex hull of finitely many points in the integer lattice. And typically I'm interested in counting the number of lattice points in such polytopes. So the number of lattice points is also called the discrete volume because it shares a couple of properties with the usual Euclidean volume. And typically I'm not only interested in the number of lattice points of the polytope itself, but also what happens with this number under integer dilations. So if you look at this example here, we have a unit square in the plane. We have 4 lattice points in there. If we dilate it by a factor of 2, we can easily count it's 9, the number of lattice points, 16, and so on. So we easily see that the number of lattice points in the nth dilate, where n is an integer, is n plus 1 squared. And since this is a workshop within the Geometry of Polynomials program, I think, or I hope, we can all agree that this is a really nice function in n, namely a polynomial. And well, it turns out that this is not just true for unit squares in the plane, but much more general. So the basic theorem of well, what is called Ehrhart-Theory is that this happens whenever you start with an arbitrary lattice polytope in an arbitrary Euclidean space R2D. So the number of lattice points in the nth dilate of a polytope is given by polynomial, and the degree is the dimension of the polytope. And this polynomial is called the Ehrhart polynomial of P, and it appears at a variety of places in combinatorics and algebra very naturally. So for example, if you want to count graph colorings, given a fixed graph and you want to count the number of graph colorings for a given number of colors, then this is given by a polynomial. One can see this via Ehrhart theory, or one can see also that this Ehrhart polynomial is a Hilbert function of a graded algebra which can be naturally assigned to the lattice polytope. And so there's a fruitful interplay between Ehrhart theory and commutative algebra in particular. And a central question in Ehrhart theory is like, can we characterize Ehrhart polynomials? So what makes a polynomial an Ehrhart polynomial? And closely related to that, can we interpret the coefficients? So I already, well, it encodes a variety of properties for sure. Like we already know the degree of the polynomial is the dimension of the polytope, but then it encodes more. So for example, the leading coefficient is always the volume. The second highest coefficient is related to the surface area. The constant coefficient is 1. But that's actually mostly what we know about these polynomials. And one reason is that the interpretation of the coefficient is difficult because in general these coefficients can be negative. And this already happens in dimension 3. Yeah? So in fact, one can show that every other coefficient apart from the leading, the second highest, and the constant can be negative. And yeah, that's kind of a problem for interpretation. So an important tool to study these Ehrhart polynomials is the Ehrhart series. So what is that? Well, we take this generating series over the number of lattice points. And since it's a polynomial, so EPN was the number of lattice points in the nth dilate, we can write it as a rational function. In the numerator, we have a polynomial of degree d, if d of degree at most d, if d was the dimension of the polytope. And in the denominator, we have 1 minus t to the d plus 1. And so this numerator polynomial is called the h-star polynomial of the polytope P. And so why is this numerator polynomial interesting? Well, it encodes us our Ehrhart polynomial in a different basis. So if we look at the vector space of polynomials of degree at most d, then we can also look at the basis n plus d choose d, n plus d minus 1 choose d, and so on. And the coordinates of the Ehrhart polynomial in this basis are exactly given by the coefficients of the h-star polynomial. And these h-star polynomials have much nicer properties. So in particular, the coefficients are all non-negative. So this is a theorem by Stanley. And he actually also showed that they are non-negative integers. So as combinatorialists, this is great for us because now we want to count something. So we want to find interpretations where these numbers actually mean something combinatorially. Or at least we want to characterize and restrict the possible h-star polynomials. So non-negativity is kind of the easiest inequalities that you can have, and there's a variety of other inequalities that are known for arbitrary polytopes. And so this is one direction of studying h-star polynomials for arbitrary polytopes, inequalities of them. And other questions include, well, what geometric or combinatorial properties imply certain inequalities that might not be true for all lattice polytopes, but maybe for interesting subclasses. And so one property that is of particular interest is unimodality, also a very natural property. So unimodality means your sequence first rises to a certain point and then goes down. But in particular, it does not have any dips. And so today, today we want to talk about unimodality of h-star polynomials for certain class of polytopes. And unimodality is typically kind of hard to prove. That's typically quite hard to prove. And but there's other properties that are stronger that oftentimes seem to be easier to prove. And one of them is log concavity. So if you have a log concave sequence, which doesn't have internal zeros, then you automatically are unimodal. And even stronger, if you have a real-rooted polynomial, then the coefficients form a unimodal sequence if the coefficients are non-negative. Okay, and so today we will see two classes of polynomials where the h-star polynomials are real-rooted, polytopes where the h-star polynomials are real-rooted. And the first question that I also announced in the abstract was, well, imagine you have a lattice polytope. Then it's very natural to ask, well, how does the h-star polynomial behave if you dilate your lattice polytope? Yeah? I mean, the h-star polynomial will also change. So how does this behave? And so this was a question that was studied by a couple of people, like Brent-Welker, Diaconis, Fuhrman, Beck, and Stapleton, who all could see that after the dilation factor becomes, when the dilation factor becomes large, then this h-star polynomial becomes real-rooted. In fact, it converges to the Eulerian polynomial. And Beck and Stapleton indeed gave a uniform bound that only depends on the dimension but not on the polytope itself. And they also conjectured that so one bound would be you just have to dilate by a factor at least the dimension of d. And what I want to show today is so that the conjecture is true and that you can actually give even a better bound. So you just have to dilate by a factor that is bigger than the original degree of the h-star polynomial. So the h-star polynomial of the original polytope to start with. So this is the first thing that I want to show. And as I said, since I also have a bit more time, I also want to talk about lattice zonotopes and parallelepipeds.
I'm sorry, the degree of h-star polynomial, is it must be always?
Yes.
Okay.
Yes.
But it can be lower.
It can be lower. Yes, exactly. It can be lower. Zonotopes. So what are zonotopes? So for the purpose of this talk, a lattice zonotope generated by lattice points v1 to vk is simply the set of all linear combinations sum of the lambda I vi, where lambda is between 0 and 1. So alternatively, you can also define this as a Minkowski sum of the segments between 0 and vi. And while a special subclass are lattice parallelepipeds. This is what you obtain when you start with k independent, linearly independent vectors. Then you get a parallelepiped. And for these parallelepipeds, Scheppers and van Langenhoven proved that the h-star polynomial is always unimodal for the parallelepipeds. And so together with Matthias Beck and Emily McCullough from San Francisco State, I could generalize this theorem and to lattice zonotopes, and we proved not only unimodality but also real-rootedness, and could give an interpretation of the coefficients. And so today I want to show you how we get real-rootedness for the zonotopes and also for these dilated simplices. And both of these classes fit into, well, a wider context, namely that of so-called IDP-polytopes. So what is an IDP-polytope? Well, an IDP-polytope has the following property. For every integer n and every lattice point in the nth dialect of your polytope, there's n lattice points in the original polytopes that, if you sum them up, you obtain this point. So it's always true that you can find arbitrary points in the original polytope, but that you find integer point is really something a bit more special. And so for these IDP polytopes, there's like a intensely studied, I would say, conjecture around an Ehrhart-Theory, which is usually referred to Stanley, but actually was also stated in the one or other way by many other people. Namely, whenever you have such an IDP polytope, then the h-star polynomial has unimodal coefficients. And we actually don't even know if they're not even, they could even be log concave. So we don't know actually. And so the most important IDP polytope is probably a unimodular simplex. So a unimodular simplex is a simplex of minimal volume, 1 over d factorial. Equivalently, you can define it as the vertices affinely span the integer lattice. Okay, and to this class of IDP polytopes, also the zonotopes belong. So, and also the parallelepipeds. So for parallelepipeds, it's actually not too hard to see. So a parallelepiped has this really nice property that if you take an integer dilate of your parallelepiped, then it can be tiled with copies of your original polytope. And that's why it's not so hard to see to obtain the integer decomposition property. And zonotopes have this really beautiful property, which was first realized by Shepard, that you can tile it by parallelepipeds. And so if you have a union of IDP polytopes, then the polytope is again IDP. So also zonotopes are IDP. And it was shown by Bruhn, Skobelazze, and Rung that also if you start with an arbitrary lattice polytopes and take a large dilate, that it also becomes IDP. So they gave a bound of dimension of p minus 1. So when you take a larger dilation factor, then you're automatically IDP. So in that sense, these two classes of example that I want to show you fit into this context. Okay. So what I want to do, so I first want to talk quickly about interlacing polynomials. I guess many of you might already know this concept. And then we want to apply results there to lattice zonotopes and dilated lattice polytopes. Okay. So what are interlacing polynomials? So imagine you have two polynomials, f and g, and f has roots s1 to sk, s1 to sm, and g has roots t1 to tn, so real rooted polynomials. Then we say that f interlaces g whenever the roots are ordered in this way. So the biggest root is the root of g, the second one is the root of f, and so on and so forth. And so from the definition, it follows immediately that, the interlacing property doesn't change if we multiply our polynomials with real numbers. And it also follows that the degrees of these polynomials are not so far apart. And the most interesting property is probably that any linear combination of these polynomials is also real-rooted. So it's not hard to see and actually follows quite easily from the intermediate value theorem. Okay, and we are not only interested in interlacing polynomials, but in interlacing sequences of polynomials. So a sequence of polynomials f1 to fn is called interlacing if fi interlaces fj whenever I is small or equal to j. And these polynomials have a variety of really beautiful properties. And probably one of the most important one is that, so assuming that the leading coefficients are all the same, let's say they're positive, then any non-negative linear combination will be real-rooted. And so this property is the key property that we want to use. And so now I hope I already convinced you that interlacing polynomials are great. But now the question is, how do we get them? And so one way to get interlacing polynomials is inductively. So imagine you have a sequence of interlacing polynomials, f1 to fm. And here we need to assume that all the coefficients are non-negative, or equivalently that all the roots are negative. Then we can construct a new sequence of interlacing polynomials in this way here. So GL is t times f1, and so on, t times fl minus 1, plus fl plus, and so on to fm. So this recursion was used by Savage and Visonti when they looked at so-called S-Eulerian polynomials, but can also be found in like a preliminary draft of a book of history. And so using these elementary properties that I've shown you before, and the fact that they have non-negative coefficients, it's actually not hard to see that this is actually true. It's really just induction. And as an observation, this sequence G1, G2 to Gm plus 1 depends linearly on the sequence F1, F2, Fm. Namely, we can multiply the sequence with this matrix of polynomials. Yeah? And so Peter Brendeen actually provided a complete characterization of all such matrices that preserve interlacing of sequences with non-negative coefficients. So, but for the purpose of this talk, keep this matrix in mind. Okay. So now then, let's start with lattice zonotopes. So, as I said, so the key property that we want to use is that non-negative linear combinations of interlacing polynomials give a real-rooted polynomial. Yeah. And so, what we want to do, so for that purpose, non-negative linear combination. So how do we calculate Ehrhart polynomials? So a naive way is like start with a polytope, dissect it into some simpler polytopes, then you know it for the simpler parts, and then do inclusion-exclusion. But inclusion-exclusion is a bit, well, it's not very practical if you want to show that something is a non-negative linear combination. So what you want to do instead, you want to have like kind of a real partition of your polytope. So no intersections. So you don't have to do inclusion-exclusion. And so one way to do is, well, you start with a subdivision of your polytope, in this case a zonotope. And so now we know that by this result of Shepard, we can dissect our zonotope into parallelepipeds. And now we take a generic point inside this zonotope, and we view this point as a light source. And now we take any maximal cell in the subdivision and look at which facets can be seen from this light source, and take away these facets. So for example, if we look at this maximal cell here, so we have it here, then what point would which facets would I see from this point here? Well, I would see this facet here and this here. Ooh. Yeah? And here in this picture, I remove those. And I do this for every maximal cell, and one can see that this actually gives you a partition of your zonotope into half-open parallelepipeds. Okay. And these half-open parallelepipeds have a really nice property. Namely because, parallelepipeds, every parallelepiped has always two parallel facets, right? And for each, it can never happen that both of these parallelepipeds, both of these parallel facets are removed. Yeah? So because imagine this point is a light source, you can either see this side, or you can see this side, or maybe none of them, but not both at the same time. And so prototypically, it turns out that all these half-open parallelepipeds are combinatorial equivalent to half-open unit cubes. By which I mean, I take a unit cube and I remove coordinate hyperplanes. And so the first step would be to understand these half-open unit cubes. What are the h-polynomials? Because then in the end, if you understand the basic ideas, if you understand the h-polynomials of these half-open parallelepipeds, then in the end, we just have to sum them all up, and then we're done. So first step is to understand these half-open unit cubes. And so the h-polynomial of these half-open unit cubes is actually quite well known, and it's related to the Eulerian numbers, or Eulerian polynomials. So what are those? So look at the permutations on D ladders. And let's say sigma is such a permutation. Then an index I is called a descent of the permutation if sigma of I is greater than sigma of I plus 1. So I is mapped to something bigger than I plus 1. And now if you add over all permutations in your permutation group SD, t to the number of the descents, then this is what is called the Eulerian polynomial. So as an example, we have this permutation here. So 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. Then 2 is a descent because 2 is mapped to 3, but 3 is mapped to 1, which is smaller. Yeah? And so in this example here, we have 6 permutations on 3 letters. And here I only wrote down the second line. And I marked the descents, the position of the descents in red. Then we see we have 1 permutation with 0 descents, 4 permutations with 1 descent, and 2 permutations with 2 descents. Okay, and so these Eulerian polynomials appear very often in combinatorics, and they are known to be real-rooted. And there's a variety of proofs, and apparently it was already known to Frobenius that this has only real roots. And so how do we see now that the Eulerian polynomials give you the h-star polynomial of the unit cube? Now for that you have to believe me something, namely what is the h-star polynomial of a half-open unimodular simplex? So if I don't have a unimodular simplex, if I don't remove any facet, then the h-star polynomial is 1. And more generally, if I remove I facets, then the h-star polynomial is t to the I. So t to the number of removed facets. So, and it's actually not very hard to see, but it would require some calculation. But if you believe me this for now, then I hope to be able to explain to you how we get the h-star polynomial of the unit cube.
For the simplex, you can do inclusion exclusion, right?
For example, yeah. Yeah.
And work out.
For example, yeah. Okay. So what do we do with unit cubes? Well, now we understand unimodular simplices. So what about we dissect it into unimodular simplices? And so one way is like, okay, take a generic point. So I will just describe to you a triangulation into unimodular simplices. Take a generic point in your polytope and order its coordinates. Yeah? Then this gives you a permutation of the coordinates. And now take all generic points that give you the same permutation, and this will give you the interior of such a maximal cell. So this is a triangulation into unimodular simplices. These are the maximal cells. And now, as I said, like it's really impractical to do inclusion-exclusion, so let's do it half openly. And one can do it half openly by saying, well, I get strict inequality whenever I have a descent. And actually, it also comes from such a decomposition by taking a generic point in the cell that belongs to the identity and view it as a light source. So one can see that. OK, and now the only thing that we have to do, well, the h-polynomial of the unit cube is the sum of the h-polynomials of the unimodular simplices, or the half-open ones. And for the half-open ones, we understand what it is. It's a number of removed facets. But the number of removed facets is exactly the number of the descents. And that's how we get the h-polynomial of the unit cube. OK. And so for half-open unit cubes, so where we remove coordinate hyperplanes, it works actually exactly the same. So you can take the same decomposition, the same half-open decomposition, and again count the number of facets that were removed in such a half-open simplex. The only thing is now, sometimes more facets are removed in a simplex. And when does this happen? So let's say I remove the first j hyperplanes, the first j coordinate hyperplanes. Well, then if I'm in a cell and sigma 1 is smaller or equal to j, then you get, like here, a strict inequality. So you get an additional descent, so to say. So let's call this for the moment the j descent statistic, which says, well, it's just a descent if your permutation starts with a letter that's bigger than j, or it's descent, the usual descent plus 1 if it's smaller or equal to j. And so one can write this down a bit nicely. So this, in fact, the set of permutation with j descents equal to k is in bijection with the permutations on d plus 1 letters with descents k and starting letter j plus 1. So what's the idea? Well, proof by example. Let's say we have d equals 5 letters and we have j equals 3, which means like a permutation that starts with a letter 1, 2, or 3 gets an additional descent. So how can I simulate this by looking at permutations on d plus 1 letters? Well, I just put a letter j plus 1, in this case 4, in front, and then I would exactly get this additional descent. And just putting a letter 4 causes problems because now we have 2 4s, but then we just move everything up once, and we won't change the relative position of the other letters. And so these polynomials, where we restrict to permutations that start with a certain letter, we call the J-Eulerian polynomials. And what we've just essentially seen is that the h-polynomial of such a half-open unit cube, where we remove the first j hyperplanes, is exactly the J-Eulerian polynomial. The aj plus 1 Eulerian polynomial on d plus 1 letters. OK. And so essentially with the same trick that we've just seen, inserting a first letter, Brenti and Welker have shown a recursion for these J-Eulerian polynomials, which essentially gives you this here. And now, again, if we think back about this lemma from Savage, Bisonta, and Fisk, this is exactly the recursion that we had. Yeah. So by induction, we now see that these J-Eulerian polynomials also form an interlacing sequence. So this was also used and actually much more generalized by Savage and Bisonta. And so as I said in the beginning, so we have to first understand, to understanding the zonotopes, we first have to understand these half-open parallelepipeds. And once we understand those, we sum them all up. And I've shown you how this goes for half-open unit cubes. And it turns out that for half-open parallelepipeds, it's a non-negative linear combination of these unit cubes. So in total, it will be a non-negative linear combination of these unit cubes. And in fact, we can give an interpretation for these coefficients. And now, since those J-Eulerian polynomials were an interlacing sequence, we obtain that it's real-rooted. Okay.
What are these interpretations roughly for these coefficients?
So if you look at the Ehrhart polynomial of the zonotope, then what you essentially do, you take, well, you sum over all independent sets of your generating vectors, and then you do
Volume?
Yeah, but like in this case, it's a different combinatorial interpretation. So you actually count the number of lattice points and so in open parallelepipeds. And yeah, so also some matroid interpretation comes in there. So it's like not a linear independent set, but it's like the internally passive elements of a basis. Okay. So then now let's turn to dilated lattice polytopes. And so for that, I want to introduce an operator on formal power series, which also has been used by other people before. So what do we do? So imagine you have a formal power series. Then what I want to do is, for a given integer r and a number between 0 and r minus 1, I just want to pick all the terms that are where the exponent is congruent I modulo r. Yeah? And then what I do to the exponent, well, I just like do n minus I divided by r. So kind of I forget that this was a multiple of r. Yeah. So the idea is to decompose the polynomial into, well, I pick just every rth term. As an example, so r equals 2, and we have this polynomial here. So what I do for f0, I take every term where the exponent is divisible by 2. So in this case, 1 and 5t squared. And the t squared, like I just divide the exponent by t. And for f1, I take, well, all the odd terms. So 3t, 7t3 to the 3 plus t to the 5. And I forget the t. And here, well, I take away 1t and divide by 2. And here I take away 1t and divide by 2. Yeah. And then have this discrete decomposition. So I didn't explain what f0 is. So f0 should be fr, 0. Okay. So, and now as an observation, so if we have such a lattice polytope P, and we look at the what is the generating series of the rth dilate of such a polytope? Well, I can take the generating series of my original polytope, and I just pick every rth element. Then I will get exactly this generating series of the rth dilate. So this observation here. And now, if one does some calculations, and that's what Beck and Stapleton did, then from this observation, one can express the h-polynomial of the rth dilate of P in a nice way that involves the h-polynomial of the original polytope. So we take the original polytope, multiply it with 1 plus d and so on to the d plus 1, and then take the every rth term of it. And so I don't write down the calculations because it's really just modulo calculus. But like an equivalent way of writing it down is in this form here. And here I have to explain what all these terms mean. So with h, I mean the h-polynomial of the original polytope. And these a's here, R, I take this polynomial, the second factor from before, to the D, and take every ith term only. Yeah, so what we have is like a linear combination of these ADs, and sometimes also a T appears, where the coefficients are also polynomials. Yeah? Okay.
Is it like a Lattice rule?
Come again?
Is it like Lattice rule?
I don't know. And what do you mean by
So
that?
like derivative of product of the functions.
Maybe not quite, but like, yeah, I mean, like, yeah, it's not hard to calculate, but I wouldn't see the exact parallel. Okay, and so it turns out that these polynomials have fulfilled also like this really nice recursion. And therefore, well, as I said, remember this matrix. By induction, again, we get that this is an interlacing sequence of polynomials. And because all these polynomials have only non-negative coefficients, we can also see that this sequence is interlacing. So what did I do here? Well, for example, ADR, R minus 1 interlace ADR, 0. But since all coefficients were non-negative, meaning that all zeros were negative, I can also bring this to the other side, so to say, by multiplying with T. Yeah. So I get this new interlacing sequence. And so this is the recall. So we saw that this is the h-star polynomial of the R's dilate. And now, what happens if R becomes big? So what happens then? What happens to the HRIs, the coefficients here? Well, if R becomes bigger than the degree of H, which was the degree of the original polytope, then I pick at most one term, right? Because I pick every rth term, so I can pick only one term. But this means that that HRI will be always like just a real number and not a polynomial if I just pick one number. And since by Stanley the h-star polynomial, the coefficients of the original polytope were all non-negative, you get that HRI is a non-negative integer when R is bigger than the degree. And since these terms here formed an interlacing sequence, it follows that the h-star polynomial of the R's dilate is real-rooted. Okay. So, and maybe as some concluding remarks, so very similar techniques applied to other situations. So, for example, Valenti and Baker, so why they studied actually these generalized Eulerian polynomials was because they were looking at barycentric subdivisions of simplicial complexes. And so Salvage and Visonti were looking at S-Eulerian polynomials, so another generalization of Eulerian polynomials, which actually are exactly the h-star polynomials of S-lecture Hall simplices. So Liam Solos was looking at the h-star polynomials of simplices for numeral systems, and also there a very similar recursion comes out. And there's so these recursions and similar recursions appear all over. And I invite you to find maybe your own nice polynomials and try out whether maybe some similar recursion comes up here. I want to conclude here.
Debating with myself whether we should do the burn type boarding question, but I think we should just stick to tradition. Questions or comments?
Concerning your last result about the dilation. So if R satisfies at least like degree of the h-star polynomial, is the Rth dilate, does that, for any polytope, is the Rth dilate like satisfies some nice property like IDP or very ample? So I'm thinking,
Yeah.
can we strengthen
Yeah.
the result if
IDPs.
R is at least dimension than IDP? But
Yeah, this was this result by Bruns syndrome. So if you dilate by a factor larger than the dimension of P, then
yeah,
oh, you
but
mean-
I'm saying, what if I replace that dimension by degree of the H star in light of this recent theorem that you have?
that I actually don't know. Liam, do you know? No, I don't know. That's interesting. Yeah, interesting geometric question.
That's a question. So is IDP like the largest class for which we think that this is true? Or
We had discussion. I said no. I think for very ample, we also don't know. So this is a bit more.
We know
The
that-
unimodal, we don't know. We know it's not log concave. Yeah.
but there's explicit examples where we know that kind of this isn't.
For the non-log concave, there's explicit examples.
I see.
Yeah.
And do you know if the class of polytopes for which this holds is like closed under Minkowski sum, or like can you?
I think we don't know. And the whole question is very open. I mean, like in 2000, like even parallelepipeds was only proved in 2013. You would think like this is a super easy example in some sense. Yeah, it's very open.
So if it is real-rooted at some point, is it real-rooted from then on? Like bigger
Yes,
lattice?
yes, yes.
Okay, so that's fine.
Like and for these dilated ones. Yeah. So it really starts at the degree of the polytope, and it's actually a sharp bound, at least when, like if you, I mean like the whole thing what I just said, like you might have realized, it actually only depends on that the H star polynomial coefficients are non-negative. So you can apply this actually to arbitrary formal power series. And therefore also applies, for example, for Hilbert series of certain rings. And but like if you restrict yourself, like if you say like for arbitrary formal power series, then this bound is actually even sharp. And if you restrict yourself to Ehrhart-Polynomials, then one can see that the bound is sharp if the degree of the original polytope was small.
Other questions or comments? Thank Katharina. So we have a 15-minute break and we resume 10:30.